So good morning, everyone. So I'm not Kavita, but it's my pleasure to introduce Helene Guerin from Université in Montréal, Université du Québec. And Helene will be speaking about competitive model for fish growth. Thank you, Helene.
Thank you, Kylian. Good morning. First, I would like to thank the organizers for the invitation to present this work in this wonderful workshop. This is a joint work with Nathalie Crel from University of Rennes in Brittany in France. I'm really happy to present this work today in front of you because you are experts in reflective processes. This is a new field for me, so I'm quite nervous. All of this is new for me. And I'm also nervous because maybe at some point of my talk, someone will raise his or her hand and will say, this model has been already studied. I checked the literature. I didn't find it, but maybe I've missed a paper. So please say it. I will be happy to learn that because indeed with Nathalie, we have not been able to go to study our first question. So I will first introduce the model and what was our motivation to study it. Studied this phenomenon, and then I will introduce our model that we wanted to study with Nathalie. Nathalie is between probability and statistic, and we wanted to do a statistical inference on this model. But we had before some probabilistic question to solve. And that is where the critical point of my talk. Maybe the answer is none, I don't know. We will see that this model is indeed a generalization of the Atlas model. Many of you know this model. And then I will speak about the well-posedness of our model. I will give some results about the existence of weak solutions. And then I will focus on the case where n is equal to 2 in the Atlas model. Not in the Atlas model, but in our model. But you can think about the Atlas model. And we will prove that there is a unique strong solution. So it is a first step, small step, but a first step. And then I will have a lot of open questions for you. many questions. So my talk is between a presentation and open problem session. So what was our motivation? We had a discussion with some colleague from Rennes, Jérôme Bujon, who is a researcher at INRAE. INRAE is a national institute in France for research in agriculture. And Fabrice Mahé, professor at Université of Rennes. And Jérôme Bujon, Fabrice Mahé, and their student Thibaut Tournade studied the rainbow trout growth in a fish tank. Their question was the following question: when is it the best time to fish the trout? The food is a cost for the fisherman. And we know that at some point, even if you had food, the growth the truth we won't grow so much. So maybe it is a good time to fish them. So I introduced some of the deterministic models that they used for their study. So if I denote by, I don't remember, yes, this one. W, the weight of the fish at time t, W max, the maximal weight, R, the maximal growth rate, and theta, the temperature of the water. They consider indeed 5 models. I just present 3 of them. So there is the classical logistic model, where the derivative of the weight is just some constant R, the maximal growth rate, times W times 1 minus W over W max. So I took those pictures from their report. The cross point comes from the data, and the red line is the curve from each model fitted with the data. So there is a logistic model. The Gompers model, quite similar to the logistic model, indeed. And the Muller-Feuger model, in their report, Bejon-May and Tournade focus on this last model, where so W, the derivative of W is W power some constant between 0 and 1 times a function of the temperature of the water. But we won't consider here so complicated, such complicated model. So during our discussion with them, what we understood is that indeed in the fish tank, there are dominant fish and dominated fish. Dominant fish eat more and grows faster than dominated fish. So if we consider a population of size n,
yeah, so just on the data, so I guess the time scale is months. So what's the average lifetime of the fish? So is it just up to their maximum weight, and as they age, the weight drops off?
it's the maximum weight of a long time. But
of the fish to
yes, exactly. Yes. I don't know exactly, but we were not able to do statistical inference. So we didn't work indeed with the data yet, because we had to prove that the probabilistic model is well posed first to work with the data. So I'm not sure about the answer. So we consider a population of size n. I did not by xit the weight of the fish I at time t. So as I said, food represents a cost for the fisherman. So the quantity is limited. There are dominant and dominated fish, and they do not grow at the same rate. So we can imagine that the growth curve is not the same if you are a dominant fish or a dominated fish. So we can assume that the growth curve, this curve BK, depend on the rank of the fish in the population. So if I introduce X with parentheses, the order statistic of the aneuplet, so in my talk, X1 is the minimum value, and Xn with parentheses is the maximum value. So here BK, I have different function BK, and the fish, the number I, will grow with the function BK if its rank is K. we added some stochasticity, which means that dominant fish can lose their status due to some various factors, illness, environmental factors. Maybe dominant fish don't behave in the same way than dominated fish to those factors. And this stochasticity allows dominated fish to become dominant. So we have added a Brownian motion, did some independent Brownian motion with a diffusion term which can depend on the rank of the fish in the population. So here is the model. We consider two sequences of function. The first one is for the drift term. The second one is for the diffusion term. So we consider this stochastic system, differential system, where Wi are independent Brownian motion, and the drift term and the diffusive term depend on the rank of the fish in the population. I will speak about fish, but I think later I will stay particular because I have also worked on model in physics, and so I will mix the word. So, and this is a state-dependent, the drift term and the diffusion term are state-dependent. If we don't consider that if we remove the state-dependent, this is the classical atlas model. And with Natalie, we thought that this has been already studied. It is a quite natural generalization of the atlas model. That is why I'm quite nervous. You are the expert of the domain. Maybe I've missed a paper, but I haven't seen this model in the literature. If someone wants to raise his hand.
What is the difference between this model and the atlas model?
In the atlas model, the sequences here are just constant. They are not curves. In this model, bk is a function. In the atlas model, bk is a constant. And sigma k is also a constant. That is the difference. So some pictures. If we consider the logistic model, so in the logistic model, bk is, as I presented before, in the deterministic model, it's bk. In this case, we assume that the growth rate will depend on the rank of the particle of the fish in the population. And for this picture, sigma doesn't depend on the rank. It's just a constant time x. So here are some pictures for only 8 fish in my fish tank. But we can see that the larger C, the more volatility we have. And we observe the interaction between the fish because at each crossing time, there is a change of drift term. We have a jump of the drift term. For the Müller-Fugger type model, so in the Müller-Fugger model, bk is a affine function at some power. And we took sigma as a power function also. And we have also this kind of picture, and larger alpha is, more volatility we have. No, this is not.
I-
I'm lost.
Another question.
Yes.
I just want to make sure, it is theoretically possible that your x's are negative, right?
That is a good point. But I can't. Yes. Yes, that is possible. But I took sigma in a such a way, in both examples, in a such a way that sigma of 0 is equal to 0. And this is important for our model, to have sigma of 0 is equal to 0. Because if it is strictly positive, then the trajectory can become negative. And for a weight, this is not a good thing. Oh, well. So the Atlas model has been introduced, well introduced by Sandro last Tuesday, if I remember well, but I will introduce it again. So the first Atlas model was the following one. All the particles, indeed, this Atlas model has been studied in finance for a portfolio. You can think that XI is the highest asset of the portfolio. I don't know anything in finance. But so the first Atlas model was the following one. All the assets behaves as a Brownian motion except the smallest one. It behaves like a drifted Brownian motion. So the first model has been introduced by Fernholz in his book in 2002. And then it has been generalized by Banner, Fernholz, and Karatsas. And they consider the case where each asset indeed, not each asset, but the drift term and the diffusion terms depend completely on the rank of the asset in the portfolio. So you have bk, some real constant, and sigma k, some positive constant. So here's the difference. In my model, bk depends on xi, and sigma k depends on xi. So I will recall some known results about the existence of a solution in the classical Atlas model. So thanks to a work of Bass and Pardue, we know that there is a weak solution of this stochastic system. There is existence and uniqueness of a weak solution. Then Fernholz, Ishiba, and Karatsas prove the strong existence and uniqueness in the case where n is equal to 2. And in a third paper, they also proved for a general value of n that there is a strong existence and uniqueness until the first triple collision time. So the first triple collision time is the first time when three particles are at the same, at least three particles are at the same position at the same time. And under a concavity condition on the second sigma, they have been able to prove that the system has no triple collision. And under another, if another concavity condition is not satisfied, they prove that a triple collision is possible. So here is the critical point of my talk. This quite natural generalization of the atlas model. Is it well posed or not? And as Chris asked, if I assume that all bk of 0 are positive, or if they are all null, if sigma is null at 0, and if there exists a strong solution, a unique strong solution, then we can prove that the minimal value is always non-negative. So all the values are always non-negative. And this is important in biology. We work with quantities that have to be non-negative. So another way to write this equation is the following way. If we introduce the polyhedron Qik, so a vector of Rn will be in Qik if its highest coordinate is at rank k, which means that Q1i means that the coordinate I is the minimum value of the coordinate of the vector. Qin xi is the maximum value, and between those extremes, you have Qik when xi is at the rank k. And using this set, we can rewrite the equation under this form. So we have a system of stochastic differential equation with a drift term bi. There is a I because the drift term is evaluated at the component I, which depends on the all vectors, and sigma I depends also on the all vectors. And this indicator functions as exactly the same. No. Well, yes, as the same meaning than before, than those indicator functions that I wrote before. So the question is the problem well posed? So we can easily adapt the proof of that in part due to the case where bk depend on the position. So if we assume that sigma k is a constant, bk is a locally bounded measurable function with at most linear growth at infinity, then using the proof of Bass and Pardue, we can prove that there is weak existence and uniqueness of the solution of this system. Indeed, we can adapt the proof in the case where sigma k is also a function, but if we want to use the proof, we have to assume that sigma k is constant in a neighborhood of the boundary of the polyhedron. So this is a quite specific diffusion term. So this is the first result. Another result is when sigma doesn't depend on the rank. In this case, the literature is quite vast. There are many, many results. I think I have wrote the weakest result in this case. So sigma doesn't depend on the rank. The drift term depends on the rank. And if we assume that sigma is a Hölder continuous with order greater than 1/2, bounded each sigma I is bounded below by a positive constant, and if bk is as above, we can prove that there is a weak existence and uniqueness, but there are also results where there is a strong existence of a solution of such equation. But maybe I've missed a paper, but in all the paper I have seen, they assume that the generator of this system is elliptic. And here is my problem. I need to assume that sigma 0 is equal to 0. So I cannot have an elliptic generator. I cannot assume that sigma I is bounded below by a positive constant. Because if I assume that, my quantity can be negative.
Why don't you write indicator near the non-zero?
Well, in the first proposition,
So you don't have rank dependence.
like here I don't have a rank dependent. I don't have it. And there are many, many papers in the literature. But what I have seen, they always assume that. And this is a problem for me. I would like to thank Tomoyuki for pointing this paper to my attention. There is a nice paper of Itkin and Larson. They studied a quite general framework. So if for a permutation tau of the set 1 to n, the discrete set 1 to n, I define this subset of Rn. So a vector x is in this subset if x sub tau 1 is smaller than x sub tau 2, etc., so on. If we denote by f sub tau the restriction of a function defined on Rn, the restriction of this function to the closure of this set, they have proved that if we consider a collection of permutation tau, if A is a continuous function on Rn such that A is C1 on each set E tau, with value in the set of symmetric positive definite matrices, if they consider a drift term of this form, so they assume that P is a positive continuous function on Rn, which is C1 in each set E tau, then there exists a weak solution to this equation. And indeed, the model I have presented before is a purely ranked model. And it is indeed a specific case of what they have studied. Oh, I forgot to tell. They also prove that there is no triple collision. But I have two problems with their results. The first one is that they assume that the generator is elliptic. I don't want to assume that. The second problem is that the classical Atlas model is not included in this result because they have this assumption of continuity on the border of the polyhedron. So it doesn't work with the Atlas model. It has been proved that there is a strong solution until a triple collision. And they have proved that triple collision is possible. In this case, there is no triple collision because of the continuity of the coefficient on the border. Yes. Yes. Yes, it is indeed. It's a symmetric, it's a matrix indeed, but a positive matrix. They assume that no, not everywhere, because if it is Lipschitz everywhere, indeed, I don't know. Because if it is, I think, yes, it is locally Lipschitz. I think under their assumption, this, because of the continuity, they assume that the coefficients are C1. So it is locally Lipschitz, and plus continuity, there are Lipschitz everywhere, locally Lipschitz. Yes, no, open, but yes, but you have continuity. Yes, the first derivative can jump, but I think, no, I know that this is, the coefficients are Lipschitz. They are not C1 on the whole space, but they are locally Lipschitz. I wanted to say something else, but I forgot. What? I don't remember. But yes, I remember. They have a quite specific drift term. This is due to the fact that they indeed prove also that the process X is ergodic and its invariant measure as the density P. Indeed, this model, the generator of this model, is essentially a Laplace operator. It is a weighted Laplace operator when we take a drift term of this form. So I didn't see in the literature the case where sigma depends on the rank and when sigma is not elliptic. So with Natalie, we decided to do the same thing that what has been done for the Atlas model, just focus on the case n equal to 2 and see what we can do. But we have two difficulties, the non-ellipticity and the rank dependency for the diffusion term. And we decided, because the motivation was a biological motivation, we decided to work with sigma that doesn't depend on the rank first. So this is a first step, a small step, okay? So we consider only 2 fish in my fish tank. I'm not a good fisherman. And then consider this stochastic differential equation in dimension 2. So W is a 2-dimensional Brownian motion. B, the drift term will depend on the rank. So the drift term will be the function B1 for the smallest particle and B2 for the largest one. And I also assume that sigma doesn't depend on the rank. So to obtain our result, we need some assumption. We first assume that the function B1 here, B2 here, and sigma are Lipschitz continuous. So even if B1 and B2 are Lipschitz continuous, B is not Lipschitz because it is not continuous on the whole space. And based on a work of Leo Bachar. Sorry? No, I don't assume that, because if sigma is bounded away from 0, it is none. Based on the work of Leo Bachar and Solyenki, I'm sorry for the pronunciation, they studied the case of d-dimensional stochastic differential equation where the drift term is piecewise Lipschitz. This is our case. But their assumptions were too strong for us. So we have adapted their proof to our case. And we have been able to prove the strong existence and uniqueness of a solution by introducing an invertible function g from R2 to R2 of class C1, such that the process g of x satisfies a stochastic differential equation with Lipschitz continuous coefficients. So if Z here is a solution of a such equation, I know that there is a strong solution, a unique strong solution. G is invertible, so X is well defined. Not the good way. So how to construct the function G? The Lipschitz coefficient is piecewise Lipschitz continuous on the plan, except that on this line, the first diagonal, when x1 is equal to x2. So we consider for some C positive a neighborhood of this blue line, theta, where we have problems. We consider n an orthogonal vector of the line, p the projection of a point of the plan on theta. So p of x is the orthogonal projection of x on theta. And we define G, and it was the idea of Leo Bachar and Solyenki. We define G in such a way, G of x is equal to x plus some perturbation, which depend on a coefficient alpha, and alpha has been defined from the coefficients of our diffusion. And this is a good choice of alpha to have. Yes. Sigma can be general. You will see. Be patient, please. So I didn't assume that we have an elliptic operator. So alpha depends on the coefficient of our first equation, and phi is just a smooth function with compact support in -1 + 1. And what we can see is that if x is in theta, it means that x1 is equal to x2. So this term is equal to 0. So I don't have a perturbation. J of x is equal to x on theta. If x is outside this domain, due to the fact that phi has a compact support, x1, the absolute value of x1 minus x2 over the square root of 2 is indeed the distance between the point and the domain theta. So if we are outside the domain, this function is equal to 0. So there is no perturbation. So J of x is equal to x outside of theta c. And we have this perturbation in the orthogonal direction of the line theta when we are in the domain. So we have this coefficient alpha. We need some assumption of this coefficient. We assume that alpha is of class C2. Alpha is bounded on R. The first assumption will be helpful to prove that J of class C1, indeed, we need more than class C1. We need to prove that we can use the Ito's formula for J, even if it is not C2 everywhere. And the second assumption is alpha bounded, is to prove that J is invertible for C small enough. So we can prove that there exists a constant C0 such that for all C smaller than C0, J defined as I have presented. J is a C1 diffeomorphism on R2. Oops. We have been able to prove that for this good choice of alpha, J of X is solution of SDE with Lipschitz continuous coefficient. So we have the result that our initial stochastic differential equation is well posed. We have a strong unique solution. And now I want to tell something about alpha. Alpha is a ratio. It is a ratio B1 minus B2 over sigma 2 plus sigma 1. If sigma 2 and sigma 1 have different roots, it is well defined. If they have the same root, for example, in 0, we just have to take B1 and B2 such that the upper term compensates the below, the sum of the sigmas. So I can assume that sigma is equal to 0, but I need to compensate this. So if I consider sigma of this form of a linear form, I cannot, with this result, consider the classical logistic model. So I called it the logistic model of type 2, because I need this power 2 here to compensate the roots at 0. So I draw a picture with 8 fish, even if my result is true only for 2. But the picture is nicer with more fish. We have a lot of volatility around the maximal value of the weight, and this is not it's quite. I think we don't see that in the nature. So we can consider another logistic type model where we kill the volatility around the maximum value. And if I take sigma of this form, I have to take B. I have to compensate. So sigma is equal to 0 at 0, but also in X max. So I can take B of that form. If I consider this case, the alpha term that I have introduced is indeed a constant. It is C2. It is bounded. It is a constant. I had another assumption on the coefficient that was, I assume that B is Lipschitz continuous and B and sigma are Lipschitz continuous. This is not the case here. But we can take the minimum value of those functions with a large constant, and we can prove that indeed the solution of the stochastic differential equation with those coefficients stay between 0 and the maximal value. So there exists a strong solution, even if those coefficients are not Lipschitz, because the solution will stay in the bounded domain. Yes?
What is their maximum?
It comes from the first question. It was a maximal value. It's a maximal weight for a truth. If you want, you can take 10 kilograms.
What is the mass of fish, individual fish,
Is a weight
for one fish?
for one fish.
So, but then you are using logistic models, these are population growth models.
Yes.
They don't make sense for an individual fish. So if you look at, for example, 2 types of fish competing for a logistic model will describe the competition between the 2 types in the population. But you're applying it to individual
Yes.
fish?
Yes.
Why is that a good model for?
We have not been able to do the statistical inference, so I don't know.
No, it's not a statistical question. So if you want to model like growth in an ecological system, you think in terms of a food web.
Because
So they compete for.
there are dominant fish and dominated fish, and they don't grow at the same rate because they don't eat. The food is limited in the fish tank.
Okay, so you think of them competing for the same resource.
Yes.
But if they compete for the same resource, then it's the size which should determine, so BK should depend on X.
Yes,
K.
but for the side, I had a problem with the side because we grow, but we can't, I don't know. We can decrease the size. We can lose weight, not
Not true.
about this. The problem is about the stochasticity. We can see that we don't always grow. Sometimes we lose weight. So I need a quantity that has a meaning when it decreases. And for the size, it has no meaning. So here is a summary of my presentation. We have introduced a competitive model for fish growth in a fish tank, which is a generalization of the Atlas model. We know that there is a weak and in some cases a strong existence and uniqueness of the solution when the diffusion coefficient is non-elliptic. In the case equal to 2, we have been able to prove that there is strong existence and uniqueness for some diffusion coefficients that are not elliptic. And now here my list of questions, but there are too many. Can we extend this result in for more than 2 fish? The difficulty when we consider a larger population is that if I consider 3 fish, so the domain theta, where we had this discontinuity of the drift term, is a union of plants, in general of hyperplanes. So it is the union of 3 planes, P1, P2, P3, where P1 is, for example, the set of vectors such that the first coordinate is equal to the second one, P2, I don't know, the first is equal to the third one, and P3, the second coordinate is equal to the third one. Okay. The intersection of those planes is a line, G. It's just the vector such that x1 is equal to x2 equal to x3. And if I take a point in the space, and I consider the plan, the orthogonal plan to this line containing my point. So I have my point here, X, in the plane. Here is the domain D in this direction. So it's an orthogonal plan to the space D. And if I draw the trace of these three plans here, I have something like that. And in the definition of the function G, I use the projection of X on theta. And the problem here is that if X is close to this plan, I can define the projection, the orthogonal projection. But if X is on the bisector plan, which projection I can choose? I have two projections. I have this one and this one. So I have a discontinuity of the projection in this case. I have some ideas how to avoid this problem because the domain theta is well known, but it is quite technical. I can describe it easily in dimension 3, but in the higher dimension, it becomes really hard. So I'm not sure that our tools are the good one to study such a question. Oops. Yes. And the other question, is it possible to extend this result to rank-dependent diffusion term? I'm okay if we assume that it is elliptic, but I don't know if it exists in the literature. But the next step is rank-dependent and non-elliptic coefficient. And the last question was our first question, but there are many steps between here and this last question. Can we do statistical inference with such model? And thank you.
Thanks, Helene. Any further questions?
Thank you very much for the talk. I was thinking if you can consider a model where you first truncate around the origin. In the region very close to the origin, you have something linear, you don't have troubles with ellipticity, and then you push something that is still elliptic after that because you already reached a plateau. So is this?
Did this morning, I was thinking, maybe I can try to have indeed a generalization of the first as class model, where only the minimal value as a drift term, but depending on the position. And the other one, the coefficients are Lipschitz everywhere. Maybe it is possible to answer first to these questions. But we were focused on our model and we didn't know what assumption we can remove or what assumption we can take stronger. We were focused on our first model, and during our work, we had this question in our mind. Maybe it is already known because this is a quite natural generalization of the Atlas model. But I asked Tomoyuki and Karazas, and they don't know. Except this paper of Itkin and Larson, but there is continuity of the coefficient, so we don't want that.
Okay, so the way I look at this is I don't see the problem with this sigma going to zero. It doesn't matter what it does because I don't believe that fish can be resurrected, which means that if X is 0, then you kill the fish.
Yes,
And you should change your model to n-1.
yeah.
And therefore, it doesn't matter what the sigma is, because then you will have all the solutions until the killing time.
I think in the examples that I have introduced, indeed the value are positive, not only non-negative. This is something we have to prove, but I think they stay positive. If we start from a positive value, of course.
So if I understand correct, I thought the same thing. Maybe you never get to 0, but still you want sigma to be 0 at 0, continuous, and 0 at 0. But the diffusion will never get to 0.
The drift term is increasing.
Yeah, but then you get existence in it?
No, because you don't have a priori a lower bound on sigma, because it can go all the way down to 0. You don't know. The minimum is,
That's not the time, you have existence in it.
yeah, maybe, yeah, I guess so.
Yes, I think there is a different way to work on this model and have different assumptions with different assumptions.
So assume that sigma is not 0 in some domain, and you assume that sigma in that domain satisfies ellipticity plus smoothness. Then
Yes,
then
there are
by
results.
then there is no at all problems for any B measurable
Yes, exactly.
by Dworkin-Vereytennikov and theorem. So maybe really like Attar or Chris told, there might be bad points, maybe not 0, say maximal weight, but it is possible that you never reach them. If you, because you have assumption like B1 minus B2
Yes.
should decay to 0. And if sigma degenerates and if B degenerates, maybe you never reach this bad point.
Maybe, but and it's not easy. It's not easy to work with this process.
And if you reach, then there is a unique stationary solution that you stay here forever.
Okay. There are no further questions. Let's thank Helene again.